Yes, thank you very much. In my presentation, I will talk about how to correlate distribution of defects, inevitable results of any welding or manufacturing process with the fatigue properties of components. Another co-author is my previous PhD student, is now working at Airbus in Germany, and I'm from a large research center located in the north of Germany, in the small city, in the small town Geestacht, and since last April we have a new name here on. We were previously Helmholtz-Zentrum Geestacht. Okay, first with regard to motivation, when the internal fracture is critical. If we look, for example, for additively manufacturing structures, we have a lot of challenges. We have here a number of stress concentration, also at the surface, also internal pores, surface roughness, of course, gradient of microstructure. However, if we consider additively manufactured parts for high-loaded components, critical for fatigue loading, nobody will apply with a surface like this. There are a number of surface treatment techniques to remove the notches or to apply the techniques such as laser shock pinning or short pinning. Therefore, then if we remove surface notches, then internal defects will play most important role, and this is also the case for very high cycle fatigue. And if we compare laser welding process with additively manufactured process using fusion processes, we will find a lot of similarities. And subsurface porosity is a common reason for internal crack initiation if sufficient surface quality, grinding, machining, or shot pinning, laser pinning, laser remolding is applied, and subsurface residual stresses are present. And additive manufacture can be regarded as a cumulative laser welding process where each subsequent layer is welded to the previous one. And if we look into the failure mechanism, we will find a lot of similarities where for laser beam welded structures, the crack were initiated from internal porosity. The same is for additively manufactured parts. So far, we performed our study for laser beam welded titanium alloy, and in principle it is applicable for other manufacturing processes. If we look for results of fatigue testing for specimens with a weld, it's a biot joint, and compare with properties of base materials, here is the base material properties represented as an curve. And specimen with a weld typically shows inferior fatigue behavior. The first reason is due to geometrical defects at fracture occurs from rod underfill. There are the typical issues, and we have also high notch sensitivity due to martensitic transformation. However, if we remove surface notches, for example, using machining process, then we significantly improve fatigue behavior. However, we're still under the level of the base material properties. And the reason is from here to here, we have effect of surface defects. And here, if we remove surface defects, then internal defects play a more significant role. With regard to fracture behavior of smooth specimens, we will find a lot of similarities, which is known for very high cycle fatigue. We have initiation from internal pores, and we have also the optically dark area and smooth area, the typical fracture mechanisms that is known for very high cycle fatigue. Cracks nucleate at subsurface porosity, and fish eye pattern on fracture surface crack grow in a vacuum-like environments because we have internal crack initiation. And similar fracture type is known for very high cycle fatigue, additive manufacturing, power metallurgy, cast, dwell fatigue, everywhere where we have internal stress concentrators. To generalize and to understand how we can predict fatigue properties, here is a schematic view of our problem. Cracks initiate from internal pores. We have fish eye area. And here is a cross-section of our loaded specimen. The pore, spherical pore is shown, and here the crack. And in principle, due to the small size of the cross-section, if the crack reach the surface, the specimen will fail. So far for us, it's important to calculate the number of cycles required to propagate in the inside of the fish eye area. And in principle, to perform any predictions, we need somehow fatigue crack propagation law. We need input data, such as distribution of our defects, materials properties, and then if we know our fatigue crack growth model, then we can integrate and obtain each point on our SN curve. For this purpose, we need a crack growth model, and especially for that kind of cracks, we need a model that considering the behavior of short cracks. So far, we have to consider the effect of fatigue crack growth near the threshold. And the challenges are input data and short crack model. First of all, we talk about short crack model. There are several approaches. In our approach, we used cyclic R-curve. Cyclic R-curve describe the behavior, the dependence of the threshold of the stress intensity factor on the crack length. And for cracks propagating from internal ports, there are also analytical approaches to calculate stress intensity factor depending on the crack length. For example, we can use this equation. And if we represent, depending on the crack length, it could be this or this, depending on the level of cyclic stress. And the cyclic R-curve describe the threshold. First we start with a lower value, and if the crack large enough, we are nearing the threshold of long cracks. And the issue is if we are crossing, we are inside the curve, the crack driving force is less than the threshold, the crack will be arrested, will not propagate. If we are in this area, the driving force is large with regard to stress intensity factor, the crack will propagate. And the condition with regard to endurance limit, it's exactly the tangential conditions to a cyclic R-curve. And there are a number of analytical equations to describe this behavior. For example, in our approach, we use the simplified equation where the R-star parameter has to be identified for our material. For this purpose, we performed testing, fatigue testing of our specimens with a weld by incrementally increasing the load level, and we accomplish fatigue testing up to the number of 10 million number of cycles. If we do not have a failure, we increase, and if the specimen failed, then we calculate this level of stress in between as an endurance limit, in principle the threshold for our cyclic stress. Here is our tested specimens. We can now analyze using the fracture investigation. This is a pore and the crack growing. And now we know the stress level, we know the behavior of crack driving force, and using the tangential conditions, we can, using the least square method, identify the parameter R star. Here is our parameter for our welded specimens. And here is our R-curve is represented, and here is the specimen with a crack arrest. What not failed, we observed some cracks in the specimen, and this is somehow identification, the proof of our concept that we have specimens where the cracks were arrested. And then we can integrate this behavior, for example, is a NASCRO equation where the near threshold behavior can be considered. And now, in principle, we can calculate fatigue properties. Here is the results of our experiments, behavior of specimens with the welds. And here is the fatigue FCP data obtained using CT specimens in order to identify the coefficients of NASGRO equation. However, if we use our model, the threshold, near threshold behavior with these coefficients, we have problem that we have disagreement. The question is why the reason. I will explain you a little bit later. Then we suggested to use a different approach. Now we have our model and we identified these coefficients by fitting our model to experimental data using the least square model. And then we obtained different parameters. And then, in principle, we can also represent what is our model will predict the behavior in this diagram. And we see, for example, in the literature, there are also data available for fatigue testing of specimens in a vacuum-like condition. You see, we have different behavior in comparison to our experimentally obtained results performed at air. And if we now calculating what is our model will predict for 500 megapascal, we have the behavior like this. The crack will be arrested, 520 megapascal cycling loading, the crack will decrease, and then will be go close to this curve obtained for vacuum, like for 540, 590. Now we can predict the short crack effect, and as you can see, our model suggests that we have to use fatigue regrowth data obtained in a vacuum-like condition because we have internal crack growth, and this is the case. Okay, now we obtained our FCP, effective FCP curve, and FCP rates for short cracks in a very slow region. Okay, now with regard to input data, in principle, if we use input data, we can perform some kind of deterministic modeling. However, if we look the now our porosity, for example, using X-ray radiography, we can perform quantitative characterization with regard to size of the pores and location of the pores below the surface. Here are our experimentally obtained results with regard to pore diameter and distance from the surface. And in order to perform some kind of probabilistic analysis, we can fit to mathematical representation of this distribution using, for example, probabilistic density function. Now the color is 2D map with regard to the probabilistic density. Here we see with the red color, the most population of the pores are located with this characteristic. Okay. Now, if we have our distribution of defects, here is our distribution with regard to distance from the surface and pore diameter. And using our model for each point on this diagram, we can calculate, in principle, the number of cycles until the specimen will fail. And now, on the right diagram, the color represents the number of cycles until failure. And as you can see, if we are in this region below, then the driving force will result to stress intensity factor below the threshold, and it means the cracks were arrested. And on each point on this diagram can be transferred to another, to the right diagram, and as you can see that the results indicates that the shortest life is not always related to the largest pore. It's somehow the competition with regard to distance from the surface and pore diameter. And if we have to obtain the condition that all pores will result, for example, to the number of cycles, we have to locate all our pores below these curves, and this is exactly the area. And using our distribution, if we calculate the area, we can perform the probabilistic analysis. And this we proved experimentally. Here are the dot points are experimentally obtained results, and the curves are what is our model predicting. And now we are able also to correlate not only the fatigue mean curve, but also the failure probability. Here are the calculated results are represented. We have good agreement, and we can obtain, using this approach, probabilistic stress number curve. Okay, I will summarize my talk, and I will show that using our approach we can correlate internal stress concentrations with the fatigue properties. Okay, thank you very much for your attention.